So this is the brain dump from the Friday lecture, plus sum, and the plus sum kind of matters. So we started talking about the fact that with the vibrational potential, the simple harmonic oscillator, we finally had a case of a real interesting potential energy, which is the parabolic black curve here. That's the V value. The y-axis here is energy, and the x-axis is some displacement of an oscillator. So we have a potential energy as the black curve, and the total energy as the horizontal red line, always a constant, so always flat. And the important thing here is that, so we have some ground state wave function psi, and it looks like more or less like this green curve. It looks like a normal distribution. And again, we solved Schrodinger's equation to get this. So minus h bar squared over twice the mass times the second derivative of the wave function divided by the wave function is E minus V. Or writing it this way, psi double prime over psi is minus 2m over h bar squared E minus V. And the important thing is that in quantum mechanics, instead of having the classical turning point be where the thing stops, thus the turning point, in quantum mechanics, E minus V is equal to 0 only says that the second derivative of the potential has to go to 0, not that the darn wave function has to stop. So that defines the inflection point of the wave function, indicated by those vertical dashed lines there. And so the wave function inflects there, and it heads into this uncharted territory. The other thing, though, is the extent of that curvature also depends on the mass. So light objects are going to have a smaller second derivative once they're into this territory where the energy minus the potential, the total energy minus the potential, is negative. So when, in other words, where the kinetic energy is seemingly negative. But all this says is that the curvature now has to have the same sign as the wave function, not the opposite sign. And so the wave function has to work its way towards 0 in this kind of exponential way. But how fast it does depend directly on not just the difference of energy and potential, but also the mass. So both of those things, the smaller the difference between the energy and the potential, and also the smaller the mass, the more you'll tend to find the wave function in this classically forbidden region, indicated with the green arrow, and also symmetrically on the other side of the other classical turning point, where in classical circumstances you wouldn't be allowed to find it. So light things venture more into this forbidden world, and if the potential isn't too much higher than the total energy, you also get more excursions into this forbidden world. So small masses make for more quantum-like things that do this funky business of penetrating into the classically forbidden region. And that's also the other factor there is that the actual energy. Somebody asked what about this business of the 0-point displacement, and that is related to the square root of the force constant V double prime divided by the reduced mass. And so the other thing that happens when you have a small mass is the actual state goes up, and the distance between the classical turning points also rises. So that's another thing. But those two are they get interconnected, but they're really separate effects. So you also will get less a wider penetration into this forbidden region for a small mass, in addition to the fact that the actual energy level will also be higher up. And then I drew lots and lots of things indicating that the potential is getting steeper, and so that's also influencing how the thing behaves. But neither here nor there. So then you can distill this into a simple case where let's consider just this double square well that showed up in the extra credit on the exam. And the idea here was that there were two valid solutions that each consisted of almost pure particle in the box solutions. They were pure particle-in-the-box solutions when the boxes were totally separated from each other. But we had a choice in the right-hand box about whether to have the half sine wave, be of the same sign as the one in the left-hand box, or the opposite sign. So we can get this kind of symmetrical or anti-symmetrical solution. But then interesting stuff happens when we lower the potential from infinity and we connect those two boxes, sort of, even if the energy level, as shown with the red horizontal line, is lower than that barrier point. So what happens is, if we consider now this solution heading toward that barrier, when it hits the classical turning point, which is that wall now, the energy minus the potential is not infinitely high or infinitely low. The potential is not plus infinity. Instead, it's some negative number. And so the function does have to curve toward zero, and it starts to do that, but it gets about halfway through, and it says, ooh, maybe I'll go back up, which is totally valid over a short distance, and then springs back into the other side of the system. And so now, instead of the symmetrical purple function when the box was infinitely high, had this hard zero in the middle, now the symmetrical function sort of tries to get close to zero right in the middle, but it never really makes it there, and it goes back up. The anti-symmetrical function, shown in green here, was identical in terms of energy when the two boxes were separated. But now, it also is going to be heading towards zero in the middle of that barrier, but it's going to hit zero because it has to change signs. It's an anti-symmetrical function. And basically, that has a little more curviness than the symmetrical purple function. And so if it has more curviness, its kinetic energy needs to be higher, and thus its total energy is going to be higher. And so the energy of the total energy of that anti-symmetrical function is going to be ever so slightly higher than the total energy of the purple symmetrical function. Those two things aren't identical anymore, and that's kind of a critical thing. And in fact, the closer they are to the top of that barrier, the more that splitting is going to be. We call it a splitting, and they'll, in fact, we call this tunneling splitting, because this phenomenon really is quantum mechanical tunneling. The wave function is burrowing into this barrier. It discovers that it can exist in there, and it also discovers that it can get to the other side. And so the system actually, if you were to prepare a system only, let's say, in the left-hand box as an initial wave function, that would not be a valid solution to the Schrödinger equation, because the wave packet, the system, would begin to discover that it could have a non-zero value inside that barrier, and it would leak through. And after a reasonable amount of time, it would assume one of the two wave functions, the symmetrical or the anti-symmetrical ones, which have, both of them have somewhat lower energy than the solution, which for the completely separate cases, because in each case there's this leakage into the barrier, and that slightly widens the regime that the wave function can exist in, and a slightly wider regime overall, because it has to be normalized, is going to result in somewhat lower curviness. Actually, any normalization would do that, correct that. Just because it's wider, it's going to have lower curviness. It's a longer wavelength, and so they're both lower in energy, but the symmetrical one, the purple one, is even lower than the anti-symmetrical one. So they go down, but the anti-symmetrical one has a node, the symmetrical one doesn't, so the solutions do obey our edict that the number of nodes should relate to the total energy. It's just in this case, the presence or absence of that node makes a very small difference in energy, but it still works, so that rule still holds. Okay, well, a real-world example of this might be something like an isomerization reaction. And this gets mentioned in the later video as well. So if you imagine some cis-trans isomerization process, and we're trying to rotate through, or if you have an eclipsed, let's just imagine we're looking at ethane, and maybe with some substituents in replace of some of the hydrogen, so there's actually an identity to the cis and the trans, or the different conformations of the substituted ethane. As the bond rotates and you eclipse the two R groups, then the energy is going to rise because they don't like each other, and so you get these kind of W wells, and that's something that the simple two-well problem from the test is more or less a simple model of. So again, you can have an energy level, rotation of sort of a peroxide, or hydrogen peroxide would be another example of this, and you can get this transition state corresponding to hydrogen atom migration, isomerization, all sorts of different cases. And again, in these situations, especially with hydrogen atoms, where the mass is very, very low, and especially when the state is not so super far below that transition state energy, a major part of the amount of the reaction is actually caused by the wave function tunneling through that barrier. So now there's one more thing to address, and that's to go to the vibrational solutions and consider it for this Morse oscillator. So we have this sort of potential where this is the y-axis is in wave numbers, and the x-axis is the internuclear bond distance, RAB in angstroms, and we're going to have a bunch of energy levels, and they're going to get closer together as you go up, because the world gets wider, because we're tearing this bond apart, and the potential is weakening. The amount of space available to the wave function increases more than it would for a harmonic solution, and because of that, the wavelength of those wave functions gets longer than it would otherwise be, and the energy goes down. So instead of being perfectly evenly spaced, the energy levels sort of start to pack together as you climb up out of the well. Now here this particular case I've drawn, say, 6 levels, and each of those steps from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6 is an allowed transition of a vibration. Now again, to get there, you actually have to be occupied. So in most cases, the only one we see is that 0 to 1 transition. But there are a lot of situations where you can find the rest of those vibrational energy levels. It can be very hot, or you can, there's a few other ways you can probe those. You can even do it by a succession of multiple laser experiment. There are what are called overtones, so there is some chance of going from 0 to 2. So you can discover the energy levels of these different states. But let's imagine for a moment that we could do an experiment, and you can, where you really go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. You can see you're basically climbing out of the well. And this gives us a way to measure the bond dissociation energy, especially important for systems that are very, very highly reactive. So we can measure bond dissociation enthalpies via calorimetry, by basically letting a reaction happen in a vessel where we can very carefully measure the change in temperature of the vessel, and then associate that with the enthalpy of the reaction by the amount of heating or amount of cooling required to have the reaction happen. But for some very reactive molecules, you can't do that. You can't put them in a vessel. You have to leave them out in free space and just fling photons at them and see what happens. And so this gives the potential for doing a thing called a Birge-Sponer analysis, which is basically to walk up that ladder and determine the bond dissociation energy by looking at the separation between those energy levels, because that separation is the wave number of the light, the color of the light that gets absorbed. So again, we have the wave number of the photon, the wave number of the light now on the y-axis, and we're going to plot the quantum number v plus a half on the x-axis. So I got 1/2, 3/2, all the way up to, say, 11/2, 12, 13/2 on the x-axis here. So it's the quantum number plus a half. We do v plus a half. It's basically the average quantum number of each step. You go from 0 to 1, and we're going to use a half. And you're also used from the term symbols to seeing that v plus a half anyway. So we measure those transitions, and because the wave number the spacing gets smaller and smaller and smaller, that means the wave number of the photon required to go from n to n plus 1 is going down and down and down and down as we walk our way out of the ladder. And the idea of the Beard-Sponer analysis is that if I draw a nice curve through those data points and go all the way to y equals 0, I extrapolate down to where the energy of the photon is nothing, then the area under that curve corresponds exactly to d naught, the bond dissociation energy. It is d naught. It's to the bottom of the allowable level. So I start there at v equals 0, and I go up to where the thing is totally broken, and that's what I've determined via this analysis, because that first point is basically between 0 and 1 for the quantum number. That's where I plot that value. Now, if this were a perfect Morse oscillator, the Beard-Sponer analysis would in fact give this perfect triangle there, and it would be quite easy to determine that bond dissociation energy from the analysis. Now, in reality, real molecules don't have quite exactly perfect Morse functions, and so especially as you get into those nether regions at the very top where the bond is breaking, you don't necessarily measure them. Well, I should say that the first step from 0 to 1 is that first point. The second step from 0 to 2, from 1 to 2 is that second point. The third step from 2 to 3 is the third point, etc. So in reality, we often aren't able to measure the last ones way down where the spacing between the levels is near 0, and there is some uncertainty about what's going on right at the end. And so, that's an element of the farther you can get, the closer you can get that thing to 0, the better job you do in actually determining this quite precisely. But if it were a Morse oscillator, it would be perfect from the get-go.